Okay, for topic 3, we're going to talk about solving rational equations again. We already know the basics, but this time we need to introduce this idea of an extraneous solution. So we're going to solve rational equations that have extraneous solutions. So first, let's just talk about what an extraneous solution is. Then we'll get into the nuts and bolts of like why and how this is going to happen for us. So first, an extraneous solution is a solution that is obtained through the solving process that does not satisfy the equation. Okay, so it's kind of like a trick in algebra. It's like this thing that you get algebraically when you solve, but then when you check your equation, you check that solution, it just falls apart. So for us, when we're dealing with rational equations, we need to remember a few things. Number one, recall. A denominator can never be zero. Okay, just can't happen ever. It's undefined. So a denominator can never be zero. And we talked about this in the very beginning of rational expressions. We talked about these values that make a rational expression undefined. So we had this idea of restricted values. So these were values for the variable that made a denominator equal zero. Well, if a denominator equals zero, the whole expression is then undefined. So thus, the expression would be undefined, which for us in math is a problem. We cannot have an expression being undefined, and it certainly can't be part of an equation. So when we're solving these equations, these rational equations, we always have to be on the lookout for those restricted values. If a solution turns up as one of those restricted values, it has to be tossed out. It cannot be part of your solution set because it would make the whole thing undefined, which we can't have that happen. So how do you find restricted values? Well, back in the first section of this chapter, we found restricted values by setting, well, let me say set, not setting. We found the restricted values, and the way we did this is we set the denominator equal to 0 and solved. So for us, we're going to have to tweak that just a smidgen for this particular section. So we know just in general, if you have a single rational expression, you need to make sure that you know what value for the variable could cause the whole thing to be undefined. And that value for the variable needs to be avoided at all costs. To find the restricted value for a single rational expression, we just took the denominator and set it equal to 0. But now with an equation, we're going to have multiple denominators. So kind of the quick shortcut for finding all of your restricted values is to find the LCD and then just set the LCD equal to 0. And any values you get from solving that, those are your restricted values. So that's kind of what I've laid out here. We have first, extraneous solutions are restricted values for the original equation. And to find the list of restricted values, set the LCD equal to 0 and solve. So when you have a rational equation from now on, first thing you want to do is factor your denominators and find the LCD. Set the LCD equal to 0 to get your list of restricted values. And then at the end, you always have to check your solutions against your list of restricted values. And if one of your solutions shows up in that list of restricted values, remember, it has to be tossed out. It cannot be part of the solution set. Okay, so let's look at our first example. So example 3 says solve each equation, check the solution. For the sake of time, I'm not going to physically check the solutions, but we are going to check our solution sets against the restricted values and make sure the solution doesn't show up in the restricted values. Okay, so first we have 2 over x plus 1 minus 5 over x minus 2 equals x squared minus 6x minus 13 all over x squared minus x minus 2. First thing I notice is my third denominator needs to be factored. So hopefully you're getting really good at factoring because we've done so much of it in this chapter. So the denominator for the third term is a quadratic trinomial. It has a coefficient on the square term of 1, so we can do the shortcut factoring. All we need to do is find factors of -2 that have a sum of -1. So factors of -2 could be -2 and 1 or 2 and -1. Okay, which of those pairs of factors has a sum of -1? Well, the first pair. So when we factor x squared minus x minus 2, we just get x minus 2 and x plus 1. So now we need to find the LCD. So I do also hope that you're getting a bit more confident finding your LCD. Rarely when you're dealing with rational equations are your LCDs going to be anything super crazy. They're going to be pretty straightforward. So we know our LCD has to have x minus 2 factors and x plus 1 factors. And then if you look at all of our denominators, x minus 2 never shows up more than once in an individual denominator. And ditto for x plus 1. They both show up at most once in an individual denominator. That tells me my LCD is just plain old x minus 2 times x minus 1. Now we need to find the restricted values, and for the sake of space, I'm going to abbreviate that just RV, restricted values. So to do that, we would take the LCD and set it equal to 0. Since our LCD is a product and that product equals 0, we would need to apply the zero product principle. That means take each factor individually and set it equal to 0. Well, x minus 2 equals 0 tells me that I would have to add 2 to both sides to get x alone. So we know that x equals 2 is a problem. And then if I have x minus 1 equals, this should be plus 1 right here. So then if I have x plus 1 equals 0, in order to get x alone, I would subtract 1 from both sides, which tells me x equals negative 1 is a problem. So the restricted values are negative 1 and 2. Okay, now I'm going to erase the work here just for the sake of I need the space, but just know how we got the negative 1 and the 2. So those values are bad. And let me go ahead and write that. These are bad. If our variable ends up being one of those values, it has to be tossed out. Remember that. So now we have done the first step for solving equations or rational equations. We found the LCD. We now need to multiply each term by the LCD. And for this video, again, I'm going to show you that kind of worked out. Solving rational equations, it's not the hardest thing you're ever going to do, but sometimes showing this step can be really helpful as you're learning what's happening. So don't stop doing this step until you're really successful and really confident in what you're doing. So I'm going to show multiplying all of the terms by the LCD. So the first term, the LCD is x minus 2, x plus 1, and I'm multiplying it by 2 over x plus 1. And then I'm going to subtract the LCD times the middle term, which is 5 over x minus 2. And that's going to equal the LCD times the third term, which is x squared minus 6x minus 13, all over x minus 2, x plus 1. So a little scrunch, but hopefully you can see it. Okay? Now for each of these three terms, we're going to divide the denominator into the LCD and see what we get. So for the first term, the x plus 1 in the denominator divides into the x plus 1 factor of the LCD one time, leaving me with 1 times 2 times x minus 2. So 1 times 2 is 2, and then we're just going to do 2 times x minus 2. We'll distribute in the next step. All right, for the middle term, the x minus 2 in the denominator divides into the x minus 2 factor of the LCD one time, leaving me with 1 times 5 times x plus 1. So let's see, we have a negative here. So negative 1 times 5 is minus 5, and then times x plus 1. And then finally, for the third term, the x minus 2 in the denominator divides into the x minus 2 in the LCD once. The x plus 1 in the denominator divides into the x plus 1 factor of the LCD one time, leaving me with 1 times that numerator. So 1 times 1 is 1, and then 1 times x squared minus 6x minus 13 is just that. So I get x squared minus 6x minus 13. Now, this x squared term tells me that I'm probably going to have something quadratic. So we want to start setting the stage for something quadratic. And remember, when you solve a quadratic equation, you need to put it in what is called standard form. So that means we want the squared term plus or minus the linear term plus or minus the constant equal to 0. So the first thing I want to do here is I want to simplify the left-hand side as much as I can, and then I'll move all of that stuff over to the right, and then we'll have 0 equals the quadratic. So let's see, we have to distribute twice. So 2 times x is 2x. 2 times negative 2 is minus 4. Negative 5 times x is negative 5x. And negative 5 times 1 is minus 5. And that just equals x squared minus 6x minus 13. So now we combine like terms on the left. And let's see, we have 2x minus 5x, which is negative 3x. We have negative 5, or let's see, negative 4 minus 5, which is negative 9. And that equals the quadratic trinomial x squared minus 6x minus 13. Okay, we're getting there slowly but surely. So now we want to go ahead and set this equal to 0. So it doesn't matter if the 0 is on the left or the right. I always move it so that the squared term stays positive. And in this case, I'm going to move the left-hand side to the right-hand side. So to do that, we're going to add 3x to both sides. And we're going to add 9 to both sides. So let's see what we get. On the left, negative 3x plus 3x is 0. Negative 9 plus 9 is 0. So on the left, we just get 0. On the right, there's nothing to combine with x squared. And then negative 6x plus 3x is negative 3x. So I'm going to write minus 3x. And then negative 13 plus 9 is negative 4. And luckily, we have a quadratic trinomial where the coefficient of the square term is 1. So this factors beautifully. Now we need factors of negative 4 that have a sum of negative 3. So that could be negative 4 and 1. 4 and negative 1, or 2 and negative 2. So of those 3 pairs of factors, which pair adds up to negative 3? Hopefully you're screaming from the rooftops the first pair. So this factors as x minus 4, x plus 1. So now we have a product equaling 0. So when you have a product equaling 0, you apply the 0 product property. So I'm going to do that kind of over here just because I'm out of space. So I have x minus 4 equals 0. And x plus 1 equals 0. So we want to solve each of these individually. So for x minus 4 equals 0, to get x alone, I want to add 4 to both sides. Well, negative 4 plus 4 is just 0, so that leaves me with x equals, and x equals 0 plus 4. So x equals 4 is my first solution. For my second solution, I have x plus 1 equals 0. To get x alone, I need to subtract 1. Well, 1 minus 1 is 0, so x plus 0 is just x. And then 0 minus 1 is negative 1. So our gut instinct says, yay, we have these two solutions, 4 and negative 1. They're beautiful. However, you have to go back to your original work where you found the LCD and then your restricted values. Notice our restricted values right here, negative 1 and 2, are bad. This value right here is bad. This is an extraneous solution. We have to toss it. It cannot be part of our solution set, because if we were to say, hey, x is negative 1, when we plug negative 1 in here and again in here, we would get a 0 in the denominator, which makes the whole thing undefined, which can't happen. So for this one, we would say our only solution is 4. So you have to be on the lookout for those extraneous solutions. And this is not the only time they're going to come up. They're going to come up again in the next chapter. All right, let's look at part B. This video is getting a little long, so let's try to wrap this one up. So for part B, we need to factor the third denominator again. So my third denominator, I have x squared minus 1, so that's the difference of squares. So remember, with the difference of squares, we take the square root of both terms. Well, the square root of x squared is just x. The square root of 1 is just 1. So this is going to be x plus 1 times x minus 1. And again, hopefully you're getting better at finding the LCD. In this case, we know our LCD has to include an x plus 1 and an x minus 1. And in none of the denominators do either of these factors show up more than once. So our LCD is just going to be that x plus 1, x minus 1. We want to go ahead and find our restricted values. So remember, you take your LCD and set it equal to 0. Since our LCD is a product, we're going to take each factor and set it equal to 0. Well, if I have x plus 1 equals 0, I subtract 1 from both sides, and that tells me x equals negative 1 is a bad value. So one of our restricted values is negative 1. And then if x minus 1 equals 0, I add 1 to both sides, and that tells me x equals 1 is also bad. Okay, so negative 1 and 1 are the restricted values that we have to be on the lookout for. Okay, so pause the video now if you need to show the steps here, but I'm going to erase the work just for the sake of space. So going once, twice, erased. Okay, so we've got our restricted values. Remember, these are bad. Okay, if they show up as a solution, we have to toss it. So let's go ahead and finish working on this, and we're going to take all 3 of these terms and multiply them by the LCD. Again, for now, I'm going to show this worked out. Once you get really successful and confident, you can sort of skip, you can't skip the step, you can just kind of do it in your head. But for now, let's just do it on paper. So we have x plus 1 times x minus 1 times 4 over x plus 1 equals x plus 1 times x minus 1 times 7 over x minus 1 minus x plus 1, x minus 1 times 8 over, and instead of writing x squared minus 1, I'm going to write the factored form. So let me make that look a little less crazy. So that's going to be 8 over x plus 1, x minus 1. And then cancel your denominator. So I'm going to do this one a little bit quicker. So in the first term, the x plus 1 cancels the x plus 1 in the LCD, leaving me with 1 times 4 times x minus 1. So that's 4 times x minus 1. For the second term, the x minus 1 in the denominator cancels the x minus 1 in the LCD, leaving me with 1 times 7 times x plus 1, so 7 times x plus 1. And then for the third term, the x plus 1 in the denominator cancels, the x minus 1 in the denominator cancels, so they both cancel into the LCD, just leaving a 1. So we're left with just 1 times 8, which is just 8. And then we want to solve. This looks like it's going to be a linear equation, so we want to distribute and then isolate our x. So on the left, 4 times x minus 1, well, 4 times x is 4x. 4 times negative 1 is negative 4. 7 times x is 7x. 7 times 1 is 7. And then don't forget your minus 8. We want to combine like terms on the right. So I'm just going to rewrite the left for now. And then on the right, 7 minus 8 is negative 1. So I'm going to get 7x minus 1. Let's see here. I want to get all of my x's to the left, my constants to the right. So I'm going to move 7x by subtracting it. Well, 4x minus 7x is negative 3x. And then I get minus 4 equals, on the right, 7x minus 7x is 0. 0 minus 1 is negative 1. Okay. Now I want to get my negative 3x alone, so I want to move the negative 4, so I move the 4 by adding it. So let's see, negative 4 plus 4 is 0, negative 3x plus 0 is just negative 3x. Negative 1 plus 4 is 3. Almost out of room, but I think I can squeeze it in here. In order to get the negative 3 and the x separated, we would divide. So I divide both sides by negative 3. Negative 3 divided by itself is 1. 1 times x is x. And then on the right, 3 divided by negative 3 is negative 1. Looks beautiful. We yearn for solutions like this. It's nice, it's pretty, it's not a fraction, it's not a decimal, it's just a beautiful integer. However, we always have to go back to our restricted values and look what shows up in our restricted value list. Negative 1. Negative 1 can't happen. If I plug in negative 1 here or here, I'll get a 0 in a denominator, which causes the whole thing to be undefined. So this value has to be thrown out. And in this particular case, if we throw this one out, so we have to say this is extraneous. Well, the only solution we obtained algebraically can't happen because it's an extraneous value, or it's a restricted value, which makes it an extraneous solution. Since there's no other value left, we just have to say that this equation has no solution. So you can do the little set notation brackets that are just empty, or you can physically write out no solution. Okay, so be on the lookout for both of these. Just know from this point forward, no matter what, if you have a rational equation, always look to see what the restricted values are and compare your solution set against those restricted values. Okay.